morning in France and good afternoon in Taiwan. Today is my great pleasure again to welcome CAP Talks. And today our speaker is Maxime Payan, and he's going to share us his PhD work on computer-assisted proof on steady state of some relation diffusion equations. And we are very curious about his work, so let's welcome him.
So thank you for the invitation, and I'm very glad to be here and in Taiwan too. So it's incredible. So yes, I will present to you my PhD work supervised by Maxime Payan. You you had already a talk with him. Okay, so it's about computer-assisted proof for steady states and also some stable and unstable states of some reaction diffusion equation. So this is a big talk. So firstly, we will focus on the cross-diffusion model. I will explain the model, get some naively approximate solutions, and use the big tool, the Newton counterage theorem. Maybe you already know something about it, and how to show how we get some theoretical solution by using this theoretical tool. And there is a specificity in the first cross diffusion model I will show you. This is the management of the non-linearities that we see on in them. And yes, and the second part is a very new part. This is a work that we just continue to yes to work to work with. This is a simpler model, but we want to understand the stability or instability of the system. And yes, we will use some big theorem, Gershgoring disk theorem, also another version of the Newton counterage theorem, and some details on it. And yes, and this is the continuity of my PhD. So the first part, the model. So this is a partial differential equation of the Kähler-Segal type, okay, with a cross diffusion and a logistic growth. So we have L, the length of the domain in 1D, okay. Sigma positive parameter is the logistic parameter. It's on the yes, it modelize the logistic growth of the species U, okay. So if there is no diffusion, you have just a logistic growth, okay. D is just a diffusion rate, the diffusion rate of V with respect to U, okay, just here. So the temperature, if you want, of the species V with respect to U. And if we focus on the second row, the dynamics on V, this is a species that U creates, okay, and it disappears in the environment at the same time, at the same rate, if you want. Okay, it's kind of chemical signal. That's why we call this system is in the chemiotaxis model. Okay, and we have the last big parameter, the nonlinear parameter, the function gamma, the motility function that is positive and decreasing. So how it acts on the dynamics of on U. So you see this is on the first term of the first row of U, and this is the cross diffusion is just there. So yes, I will draw something maybe up just to visualize gamma a little bit. So gamma is a positive decreasing function. We have something like that, okay? And it's close to 0 when So when V is very high, we have something, so this is gamma and V, okay. We have something very close to 0. So it means that this term completely disappears when V is very high. So it means there is no diffusion of U. So there is just a logistic growth, okay? So V very high, U very high, okay? And on the contrary, in the other hand, when V is very close to 0, because all the quantity is positive, gamma can be a constant, okay? So just a simple diffusion, okay, with some rates, or maybe infinity, okay? And we have a very high diffusion rate for U, and it means that when V is nowhere, okay, you look for just spread in the environment very, very fastly, very quickly, okay? So we have just this, okay? So we just the explanation of the model. And here we are interested in the long-time behavior of the solution. So we will focus on um, the stationary equation. Okay, so we just forget time. Here the functions u and v does not depend on time, and we will look for solutions of this equation. Just a remark: for all sigma, we have u equals 1, v equals 1. Is a solution of this stationary equation. This is a property we will see again just later. Okay, so we have this. There is a big tool we can use. This is the Fourier series, okay? And because we have symmetry at the Neumann boundary conditions, we can look for solutions just of sum of cosines because of this the geometric justification just here. And then we will we will denote the sequences, okay, the Fourier sequences. So just the coefficients of this series with the bold notation, okay. And there is just a naive of notation for gamma v, okay. Gamma v will be the Fourier sequence of gamma round v, okay. And it's an object a little bit complicated to understand, but we will manage it just later. So now we pass through all the stationary equation to the Fourier Fourier coefficients, and we get this equation to have to keep in mind, okay? So the multiplication becomes the convolution, standard convolution, and we have this non-linear equation on a sequence space. But it can be written as a zero finding problem, and it's very useful for us. And the first thing naively we can do is to solve numerically this problem with the standard method for a zero finding problem, the Newton's method, the well-known Newton's method. So what do? We just calculate item by item the derivative of f in the vector uv, okay? So infinite sequence, but naively we can truncate them. And we have this, this object, a matrix of vectors. And then we just apply the Newton's method. We compute the sequences of those vectors with the inverse differential of this applies to this, etc. And there is no problem. We start from a good guess of something interesting, of course, and we call u finite the last iteration we choose when we don't go when two iterations are very close, okay. And for example, we have this illustration. So I fix the model with sigma equals to 0.25. Gamma is a rational fraction here. The diffusion rate of V is just 1, and the length of the domain is 3 pi. So on the left, this is the U0 of the Newton's method. Okay, I call it a perturbation of the trivial state. So I just put some coefficients on the first first coefficients of the sequence. Okay, and the representation with the sum of cosines, and on the left is the last iteration, and you see it's just kind of cosine, so it's not so interesting. Okay, so we to get something on the dynamical more interesting on the dynamical of the system, we will use another method that explore the numerical space solution. And this is so I will explain. So we get back to the sequences equation, okay, with the Laplacian and bold notations and the convolutions. And we are looking at sigma as a new variable. No longer a given data. And we pose f tilde such that f tilde sigma of capital U satisfies the same, exactly the same equality. And then we denote tilde capital U index 0, just the capital U with the new variable, okay? And then we take delta, an exploration step. So we compute a tangent, unitary tangent vector to the curve f tilde u tilde equals 0 in u tilde 0. It's a unitary vector in the kernel of the differential of f tilde u tilde 0. And then we denote g0 u tilde, the functional just there, okay? And we look for a 0 of g0. And if we have a 0 of g0, it means on the last rows that u tilde is a 0 of f tilde, so it means it's on the curve, okay? And on the first row, this is just a real number, it means that u tilde belongs to the hyperplane directed by v0 tilde and centered in u0 plus delta v0 tilde. So if I made up that, if I made up, sorry, I made a little drawing. I don't have so many places, so I will present to you the next slide. So okay. Up. Okay, so here this is the illustration of this theorem. But before that, I will explain a little bit the method in the last slide. So in the space, I start with u0 tilde, okay? And this is the curve that I don't know, okay? This is f tilde u tilde, okay? I compute a tangent vector v0 tilde, and I take the point u0 plus delta v0, so this is the length delta, and I take the hyperplane, whoops, sorry, this hyperplane, and I look in this hyperplane the points on the curve, and you see it can be this one, okay, and this is u1, sorry, u1 tilde. Okay, so I repeat this to get this big diagram, bifurcation diagram. So on the abscisses, this is the sigma, okay, the first element of the U tilde vector. And on the ordinals, this is a projection of capital U. This is just the y-intercept of the little u, okay? Just a choice of projection. And so in the little green points are just the U tilde index k, if you want, the numerical solution that the algorithm of numerical expression find, okay? And I started from this point, okay, this little point in abscisses 0, ordinals 1, and it starts, and it goes further. And when there is a cross, it's denoted by a purple circle, and the algorithm can find those kind of change of direction, okay? And it takes the three or more direction the algorithm find and continue this. So here we have around 6,000 points, and it's yes, it's quickly we quickly get those numerical solution. Okay, so here this is the many steady states we can have from a simple system. Okay, so there is another diagram. This is exactly the same, but be careful, I will change the projection. So in abscisses, in ordinals, this is u of x equals to 0, and I will change it, and this is, I unroll, if you want, the film in space. So it's a little bit weird, but it's interesting for us to get something on the dynamical and this 3D object, okay? So firstly, we have the property of there is many solutions for all sigma equals to 1, okay? Yes, for all sigma, sorry, there is u of x equals 1, that is a solution. This is this straight line in ordinals equals 1, y equal 1. The question of crossing, okay. So sometimes in 2D, because of the projection, we are not sure there is a crossing. So yes, here there is one, etc. But here this is not a crossing, etc. And there is a third property, interesting. The curves that rotated, if you are closer to sigma equals 0, you're rotated faster than you are far from 0, okay? So this is a little bit complicated to see, but there is this phenomenon, okay? The system is more and more, with significant variation when sigma is close to 0. Okay, and you have, of course, some cross line from these different curves. Okay. So now the question, oh yes, also you can have some solutions from literature, okay? This is a solution that I refined from an article of Wang Xu with another motility function, more complex one, with the inverse of a rational function, the exponential. Okay. So now this is the question of how we can get theoretical functions, because all in green was numerical solutions. So we put theoretical framework. We take a Banach algebra. This is a L1 weighted Banach space, sequence space, with this norm. Okay, just weighted nu in the norm, and we compute everything we need in this space. But there is a big problem. We do not know how to literally inverse the operator. If you have the Newton method in mind, there is a differential of f in a vector inverse applies to f of u. And this inverse, we do not know in this infinite dimension space. We don't know how to inverse it. We don't know if it's invertible. Okay. So to continue to get some conclusions, we will change a little bit this functional of the Newton's method and apply fixed point argument on the new functional where we replace the differential of f inverse by a matrix, an infinite matrix A that approximates that approach the inverse of the differential in a finite approximate solution, and with A injective, of course, because other else we do not have or a fixed point of it. It will not be a zero of f. Okay, if A is not injective. And also combine numerically calculable and satisfying the hypothesis of the Newton counterage theorem that I show you just now. Okay, so the big tool we use, maybe you are already familiar with it. So let nu strictly bigger than 1, so we just take the planar space we want. Assume there exists y, z1, and z2, and r star non-negative, positive. So y, z1, and z2 depend on A, okay, the matrix A. Satisfying 5A means that U bar is a very good approximation of a zero of f, okay? But I recall that U bar is finite, very important to compute. So y will be very small, okay? 5b with 6a means that the functional is a contrasting map, okay? And 5c with 6b means that the functional is a contrasting map from a ball into the same ball, okay? And it ensures that also 5c ensure that the neighborhood of the finite approximate solution f is not singular on it. And then if we have this all inequations, we have a unique solution u star in the neighborhood, in the known neighborhood, and the u star is solution of the sequences equation, and the functions u star v star described by the Fourier sequences, the vector u star v star are solutions of the stationary problem, and we have the theoretical solutions we want. Okay, so now the question is how to get those hypotheses satisfied. So firstly, there is the choice of A, and then the computations of y, z1, and z2. And yes, so the choice of A, the approximate inverse of the differential. So according to a work that Maxime Payan did, we choose A like that. So this notation means, so the 2 by 2 form is from the system of two species, okay? So if we focus in one block, we have a top left quarter that is a known finite matrix, okay? And the tail this operator is an operator on sequences. Okay, but here this is a yes. Yes, on the tail of sequences. So the Aij are from the inverse of a finite dimensional projection of the differential of u bar v bar. Of course, okay, we want an approximated inverse of the differential of this. So somewhere we need something close to the inverse, okay, and this is here. And here the Aij are computed by the computer, okay, and the tail part is computed by hand by the mathematician, and morally these terms are the inverse of the main part of the differential of this of df, okay, of this matrix, okay, infinite matrix. And by hand in this problem we have the that it can be written as a weight, a vector weight w, that is the inverse of this matrix in the sequence in the Banach space. Okay, so here we have in each block two parts, a finite part that we know and a tail part that we not know exactly, but we can ensure the behavior in the asymptotic way. Okay. So now we got this A. We need to understand the big things in this problem, the nonlinearity. Okay, because everything I wrote just before, there is a gamma somewhere, and also in the differential there is a derivative of gamma. So we need to understand how to pass through gamma with Fourier sequences, because we do not have a full expression of gamma in Fourier sequences. Okay, we do not know anything on it. And in the literature, there is many types of gamma, polynomial, power series, rational fractions, and we want to manage all this case, of course. So, two questions. Given an analytical expression of gamma, can we find a good approximation of gamma applied to a finite vector? We will call this good approximation gamma underline, okay, in the Banach space. So this gamma underline is a finite known vector. Okay, and the other question, when we have an approximation of a vector, okay, can we estimate the error between the approximation and the real object we want to know? And also, because of the hypothesis that to get the bound Z2, can we bound the value of the norm of gamma v for any v in the neighborhood of a finite vector? And there are two very common ideas, but recycled, if you want, in this context: the Taylor expansion and Neumann series. So I will show you how we do that. So firstly, just a toolbox. When we have two vectors in the Banach space, we assume that we have underlined approximations, okay, and with errors. So of course, when you sum the theoretical all the vector, a good approximation is the sum of the approximations, and the bounded error will be the sum of the bounded error, no problem. For the convolution, the convolution of two entire vector, a good approximation is the convolution of the finite approximation vector, okay? And the error will be that. So you see here, it depends on the norms of the finite vectors. So it can be, the error can be very high here. And the last one, it's little Neumann thing. If we have a vector such that we call it A, such that this inequality is satisfied, it means that X is invertible in the binary space, and we have that A is not so far off X minus 1, and we have this error bound. Okay, so we put that to get the answers of the two questions. If we have an analytic expression of a function, any function, we can of an entire function, we can truncate it, and we sum, etc. And by the Taylor inequalities, we can find the error bound, and with also a little Taylor expansion at order 2, we get this local bound, okay? And then with such tools, we can manage any product and division of any power series of polynomials or polynomials. Okay. Some examples that are used here on the system we choose. So the rational fraction 1 over 1 plus x to the power 9. So what do? I take a finite vector, I put it to 9 convolution of it. It's a finite one. I just add the vector 1, 0, 0, 0, 0, 0, okay. I look for a vector that inverse this one. I call it A, and I have an error bound, this one, okay. And for 1 plus exponential, this is an entire function. I truncate it to index k minus 1, and I have by Taylor expansion bound on it. And also, I add some local bounds from Neumann and Taylor. Okay, so be careful here. In the example of exponential, I didn't use the functional of the article of Wang Xu. This is not exactly the motility function. This is the inverse one, but it was too large to write the full motility functions and in example. So I just make the choice to show you the denominator of the real motility function I used. Okay, so now we can compute the bounds. So that depends on A and gamma, of course. So this is just a quick parenthesis, and I show you the simplest bounds. Why? Okay, but what do you have to keep in mind? It's the discriminate the finite and the tail part. Okay, so for y, of course, this one is a finite vector applied to a matrix we know exactly, but there is a tail part, but it disappears when we multiply it by a finite vector, so there is no problem. These two norms are known by hand, okay? This one, the norm of u bar is completely known. This is a finite vector, and the norm is known. And at the end, there is the error on the motility function we made because of this one. Okay. So yes, and for each bound, you split between what we know, what is in tail, what is with errors, and you spread it by inequality, the triangle inequality, and you get it. This is a little bit technical, but yes, if you are interested, we do this work in the preprint with Maxime Payan. Okay, so now we can apply, we can get some theoretical solutions. So I remind a little bit the method. So get a numerical approximation by a Newton's method. yes, completely easy, but you are not sure that you get an interesting solution. So to get many steady states, you can use a numerical continuation, okay, to get this big diagram. And then you can apply to every numerical approximation the algorithm to that checks the Newton-Coleridge theorem. So you have this point, the numerical approximation. You compute the approximate inverse of the differential of f in the finite point using the toolbox, so gamma, etc. Then you compute from A the bounds y, z1, and z2 by construction they satisfy 5a, 5b, 5c from the Newton-Coleridge theorem. Then you check if you have 6a, 6b, and 7. And if they are satisfied, you can say there exists a unique solution in the neighborhood, in a known neighborhood of the numerical solution approximation. Okay, so here we have the theorem for the Wang-Xu function. Okay, so I repeat the datas. And yes, there exists a smooth steady state UV of the Keller-Segal equation for these datas, such that the theoretical solution is near the numerical approximation about 10 to the power minus 12. So this is very, very close. If you want, the figure 3 is the theoretical solution because this number is yes, it can be seen on the plot. Okay, it's too tiny to be seen this margin on the plot. And to make the proof, I take a number of Fourier coefficients, 100. I take the Barnard space. I want to compute the bounds, and yes, I take a standard radius, okay, and with the toolbox and some calculations made by hand and by the computer with MATLAB and the library IntLab for arithmetics, interval arithmetics, we get y equals to this number, z1 indeed smaller than 1, and z2 not too big, okay, and we check that we have the hypothesis of the Newton-Coleridge theorem, and then we have the existence and uniqueness of our theoretical solutions. So now I check the algorithm of theoretical solutions for yes, for any point of the diagram in the precedent figure, and yes, the theorem is that for those 6,000 points, there exists a unique theoretical solution in the hair R neighborhood of with R equals to 1, 10 to the power minus 8, and we have exactly this. So it informs us on the dynamical of the system and show that the behavior of the system is exactly that. Okay. Yes. So now, yes.
Maxime,
also,
Maxime, can I ask a question?
Yes.
Can you go back? Yes. So is there any difference if you want to obtain a solution near the bifurcation point?
Yes,
In your
but
method, do you encounter anything like maybe the convergence rate is too small or something different? Or they
yes,
are all the same?
yes, you're right. In the bifurcation points, I valid there is a validation because I'm too far from it. Yeah, the validation, the bifurcation point will not be validated if I'm exactly on it. Okay.
Okay.
And because of the step is just rough, okay, I did not encounter the cross exactly the bifurcation point, okay. That's why there is no problem here. But if you give me the exact point in the bifurcation, it will be not satisfied because the differential is not invertible. So the A will be completely
Yes,
infinite.
exactly,
So
yes.
yes, it's a good
Okay,
question.
I see. Thank you.
And also I take a slice in sigma equals to 0.0, I don't see it, 53. And you see that we have many different stationary solutions for the same sigma, and it informs you about the the, the behavior you can encounter if you you evolve your system. So the question at the end of this study is how we can understand those steady states, how we can took the first solution and not the last solution. What is the behavior, the temporal behavior behind this? And the first step is the question of stability and instability of this. So we will ask this question to a simpler system. It's this non-local diffusion system. So this is a question that some colleagues ask us to analyze this system. So it's a simpler one because, as you see, there is just diffusion of U. U is created by disappear, okay, because A is negative, and created by V because B is positive. Diffusion of the second species created by U disappear at a rate D, and there is this non-local term, okay. I2 and I1 are two segments of 0L, okay, of the segment 0L, and it means that we take the mean of it's one I2 here, sorry. We take the mean of the species U in a part of the environment, and we bring it to the location I1, okay, for V. Okay, it's kind of yes, non-local diffusion, that's why. So here we use exactly the same tools, okay. So we take it through the Fourier sequences, and we get this one. So here the sequences depends on time, okay. And B will be the operator that, yes, that the linear operator such that we have exactly the translation of the spatial to the Fourier, okay. And this is completely linear, okay. So that is very good for us. It will be simpler for us, okay. No things to manage with nonlinearities and errors, bounds, etc. So it will be simpler. So we can rewrite.
So Maxime, before you proceed, can I ask a question? So in your talk, you always use Fourier basis, right?
Yes, exactly.
Yeah, because you have bounded interval, non bounded condition.
Yes,
But
exactly. This is why.
in Olivier's talk, he claimed that the Chebyshev basis is at least it must be better than Fourier basis.
Maybe it's a work I did, but I know that Maxime, Braden, Olivier Hainaut, and all the community use other bases in other models,
Yes.
but I'm not familiar with them, so I don't know the advantages of
I
this
see,
one.
I see. Because my question is in in principle, it's a Fourier basis is the only choice you can use, or there are other choices. But Fourier basis is definitely the most natural one, I think.
Yes, yes.
Okay.
And the structure that gives is very useful.
Yeah.
So that's why we choose them. So yes.
Yeah. Okay. Thank you.
Thank you. So yes, so hope we rewrite the sequence system here as a linear system. So we have dt capital U equals to the operator M applies to U with this time U is not U next V, this is U0, V0, U1, V1, etc. Okay, be careful. This is not exactly the same basis we choose, just a little change. And M is this operator, okay? So see it's 2 blocks by 2 blocks, okay? And we have, of course, the second derivative in cosines that appears in diagonal, okay? And there is those B terms that are these non-local things. There are infinite of them, okay? So be careful. And then the question of stability instability is translated to the studying of the spectrum of M. Of course, remind if you have one positive eigenvalue, it means that in long times the solution will go into infinity. This is completely unstable. Okay, and if all the eigenvalues are of negative real parts, you have something stable, linearly stable. Okay, so how to study the spectrum of M? So the first idea was, oh, there is a big theorem that localize the spectrum of an operator of a matrix. This is the Gershgorin disks theorem. So when we have an operator written like infinite matrix, this is important, we can denote the radiuses that are the sum of a row except the diagonal term, okay? And the disk will be the diagonal term in the center and the radius of the disk, of course. And the theorem affirms that for any eigenvalue of M, there exists a disk where the eigenvalue is in it, okay? And furthermore, if the disk is disjoint from all the other disks, then there is just this eigenvalue in the disk. The eigenvalue is isolated from the others. Okay, so there is some literatures on the spectrum of infinite matrix. Okay, you can see those references just after. So we will apply quickly, naively, this theorem to a truncation of the matrix M, and we get this. So we just truncate to a length of sequences about 20. So be careful, the matrix M index n will be of size 40 by 40, okay? And we take those parameters here. So what we see, this is the spectrum of M. So we see here not something we do not know exactly, but we see some disk goes to minus infinity. They are small, okay, but I didn't zoom on it. But in those disks, there is another disk, so we cannot apply the localization, the isolate things in the theorem. Okay, and in zero, we cannot discriminate between an eigenvalue can be positive or negative. So we cannot conclude about the stability of the system. And also a quick analysis gives that the radiuses goes to infinity and I goes to infinity. So there is a little problem. So yes, naively, it doesn't work exactly how we expected to, of course. So we analyze these two problems. So the radii comes from the operator B, okay? The B index AJ are smaller than C over AJ, okay? And the harmonic sum appears and in the radii, and this diverges, of course. And also, the fact that the circle crosses is because of M is not diagonal, okay? So to get more accurate information on the spectrum of M, we will make a change of basis that corrects these two things, okay? The spectrum, of course, doesn't change if we change the basis. Just the row, the vector, or the eigenvector changes. So we can B, okay? We take Q, an infinite diagonal matrix, such that we got 0 everywhere except on the diagonal, of course. And on the diagonal, the first block will be 1, 1. The second will be 1, 1 also. The third one will be 2 squared, 2 squared. Then 3 squared, 3 squared, etc. Okay. And then we look at the this new matrix. So here we will change. We will not change the diagonal block, okay, of M. So it will change just the B coefficients on the lines and the rows, okay. So it's we multiply it by what we want, and then we diagonalize this matrix QM Q minus 1, but just we diagonalize it, a truncation of it, okay, and we completed it by the identity, okay, and we will shrink the disk, the first disks. Okay, so yes, so now we have to compute the centers of this new matrix M tilde, okay, and the radius. So what we have is this. The first centers for an index of the row smaller than n is approximately the ith eigenvalue of M, okay, because we take almost diagonalization of M index n. So we expect to have this, but we are not sure, okay? But this is a single real number that the computer gives us, okay? And the last centers will be the diagonal elements, and it doesn't change by P and Q, of course. And this is this one. So its behavior in I will be in squared I, okay? And the radii bounds, I can compute just bounds of the radii, and it's sufficient to conclude. The first radii is their behavior is yes, is in n squared, okay. For for I bigger than n, there are some exact radii because of the structure of M, and this one, this for the other radii will be this computation, and its behavior is like A prime, okay. So it will be important, and we call capital R index I this bounds, okay. So now I will apply the Gaussian theorem with those centers and radii bounds, and we get this. For the parameters fixed, we have for any n and delta, the spectrum of M is included in the semi-plane where we have the maximum of the radii bonds plus the centers. Okay, it's on the left part of the plane, and the union of the disk. Maybe they are disjunct. We expect this. So I illustrate it just here. So here I apply exactly this theorem, and what we get is little little disks. Okay, this line showed the maximum of radii bonds plus centers when they are far. Okay, when I is very high. And yes, so the spectrum is included in the left part, on the left on this line, and in those isolated circles. Okay, and the question is also the stability. So do we have a circle on the left or on the right of this y equals to 0 line? And if we zoom, so here there are 40 circles. Okay, here there are 4 circles. Okay, so the radii are very small, and here this is the first circle, and you see it's negative and there is no problem. And this is a theorem. Okay, there exists an eigenvalue that belongs to these little disks. Okay, and other one also. And then I apply the same equation 12, to delta equals 4, and I have another spectrum. So 40 disks. You see that the maximum is bigger, okay, because the delta is bigger. So the spectrum is included in the left part and in those isolated disks, okay. So I zoom on the 5 first circle and the first one here. So conclusion, there exists an isolated eigenvalue of a positive real part. Okay, so it means that the system is unstable. Okay, this is exactly what I said for delta 1 and delta equals 1 and delta equals 4. And the question is, this raises the question, do we have the same conclusion for every delta belongs to 0 and 4? And does exist a delta? Because if you, there's a problem, okay, you cannot be stable and unstable at the same time. So does exist a delta star for which 0 is the biggest eigenvalue? Exactly, okay? And is it unique? Maybe you can cross many times 0, okay, I don't know. And I affirm that yes, there exists. So I will be very quick on the demonstration of it, but there is 3 steps. The first is apply Gagarin theorem to any delta with interval arithmetics. We get this figure, so yes, and there is just, so the each point means there exists a unique isolated first eigenvalue, okay? And green, this is concluding on the sign. So yes, this is indeed on the left here, and here this is indeed on the right. And there is just a little red part here, and it means that we cannot conclude on the sign of the first eigenvalue, but we know this is isolated one. Okay. So now I will use a Newton counterage theorem to refine this little red part. So it's an adapted one, a simpler one. Okay, there is yes, Z2 bound simpler than the problem before, because this problem, if you want, morally is quadratic in x. Okay, x, the lambda u vector. But this is exactly the same. We apply this theorem to get, well, yes, of course, we choose A before that, okay? exactly the same idea. We take a truncation of the differential, we take the inverse, and we complete this with the morally the inverse of the main part of the differential of the function we want. I computed the bounds. Here they are a little bit simplified, but the idea is here. And we apply to get this theorem. So this is the red part we just saw before, okay? And here we affirm that for any box, any rectangle, there exists a unique eigenvalue near the centers of it, okay? And thanks to the precedent theorem, we know that there is isolated. So in each box, there is an eigenvalue, a unique eigenvalue, okay, for each delta, okay. So there is, yes. But it's not conclusive for these three rectangles in the centers because 0 across these three rectangles. So there is another problem. We need to understand something more on the behavior of the first eigenvalue with respect to delta. And the third idea is the implicit theorem. So yes, thanks to the implicit function theorem and some calculations, we can write the derivative of the first eigenvalue of m with respect to delta. And we have this simple expression. This is the A, but we remove the even rows and columns times B times U star, so the solution of Newton-Coleridge theorem here for the delta parameter. And we apply this to get the last theorem, and we have the derivative of lambda with respect to delta, and we see that this is completely positive, so it means that the growth, yes, lambda grow with delta, and it means that yes, we can conclude with this theorem by using the intermediate theorem. So a little recap, and I finish. Gershgorin theorem gives the theorem 3 and isolated first eigenvalue for any delta from 0 to 4 with interval arithmetics. Newton-Coleridge gives a knowledge on the curve lambda of delta with precision. We have exactly this inclusion, okay? So it across 0, but we do not know there, and maybe many times. But implicit theorem gives theorem 5, give a knowledge on the derivative of lambda with respect to delta, and say that no, it grows strictly. So by the intermediate theorem, we can conclude that there exists a unique delta star in 0.5, the 0.4, sorry, almost equal to this number, it's not important, such that for all data before delta star, the system is linearly stable. It means that all the eigenvalues are negative, real part. And for all data bigger than delta star, systems 9 is linearly unstable with one positive eigenvalue here. And yes, conclusion quickly. Yes. Yes, the computer assisted proof method is yes, a good way to analyze some complicated system, complex system. And yes, I will finish just there.
So thank you, Maxime. Thank you for your very nice and detailed talk, and also give us so many nice applications. Thank you. Yeah. So questions, comments, remarks from the audience. Just unmute your microphone and ask. So let me begin, maybe one question. So, can you determine the multiplicity of eigenvalues?
Can you
People are interested in the, for the multiplicity. Yes.
can you repeat, please? I didn't understand.
Like a multiplicity, I mean, are all your eigenvalues isolated and algebraic simple? There's an algebraic multiplicity and the geometric multiplicity of eigenvalues.
I don't
Yes.
know what is multipiece, but
Like for example, if you have a matrix and lambda is an eigenvalue, if the characteristic equation it has a lambda minus something a square, then the algebraic multiplicity is 2.
okay, yes, okay. Yes, here, yes, I can, yes, in the theorem of Gershgorin, the eigenvalues are counted with multiplicity. So now we cannot detect the multiplicity of an eigenvalue in the infinite matrix. No, we cannot, but maybe we can detect it numerically, but here the question was not asked, but yes, but I think there we can find a way to detect the multiplicity of it.
Okay.
But here it was not the question, and the question was just if there exists an eigenvalue of positive parts.
I see. Sure.
But yes.
Yeah.
But I think it's possible numerically to detect and maybe theoretically to affirm. Okay.
I see.
The
Yeah.
Newton-Coleridge theorem, maybe.
Because multiplicity usually you consider derivative of your operator, further derivative, so you can still reformulate this. Okay, good. Yeah, good. So questions, comments? But okay, maybe can you go back to your slides about the weekend B and there's a Q and B slides.
The changes basis.
Yeah, you change the basis. I think this is a super smart because somehow there's a convergence issue, but you change the basis and then you have a good estimate. Can you tell us the intuition or motivation of considering this basis?
Yes, the problem we saw was the fact that the operator
Yes.
B was not yes kind in the in this, and there is this harmonic sum that appears. Okay, and the fact we doesn't want to change the diagonal because it was good for us to get this minus a squared. Okay, because it's when you inverse it, there is yes 1 over I squared, and when it goes to infinity, this is very nice. So the question was, okay, I want to get, when I sum a row or line, I want to get something that converges. Okay.
Yes.
So we just multiply it by a squared. So it's exactly we take exactly in rows the sum of uh, j squared, 1 over j squared, okay, with above I, just an I. So it's perfect. So we have, yes, of course, in rows, you get a constant bigger and bigger, but you 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 know that each radii, when you fix the row, is finite. So it was perfect. And for the diagonalization, it's just to get very, of course, very smaller radii for the first eigenvalue. It was just something like that. And yes, it's a little bit complicated to when you compute radii bands, because there is many constants. Just yes, the row something depends on this change of basis of P, okay?
Yes.
But they are completely finite and does not depend on N. So it was perfect. So this change of basis is, yes, not very important, okay? You can
Okay.
apply directly on Q and Q minus one, and you already have something interesting to localize the spectrum, okay?
Mhm.
But yes.
I see. I see. So M is essentially from your Fourier basis.
Yes.
Q is somehow you want to make your low sum
Yes,
of terms finite.
it's weird because Q is yes, it's infinite matrix with terms goes to infinity,
Yes.
because we just make a change of basis
Yes.
by Q and Q minus one,
Yes.
it completely disappears this problem. Okay,
Mm.
so it's just a new weighted basis. Okay, not
I see. I see.
Fourier basis, but we put a squared to each coefficient if you want.
Okay. I see. Yeah. Thank you. Yes. Other questions, comments? Mm. So I am so curious. So can you go go to your next slides? Like no, in preparation. Yeah, because before this slide, I also had a question. So
Which one?
next, conclusion
Yes,
there.
yes, I go further.
Yes. So the last one is a study the stability of steady state in the closed
Yes,
diffusion model, right? So today you can study the stability of steady states in a linear non-local problem.
yes, yes.
So
Indeed,
at
the
that time I
further
was wondering, maybe you can also study the stability for the closed diffusion model, but in the end, no, this is ongoing research. But why? What is the main difference?
yes, there is the management of the non-linearity,
Yeah.
and here what I used is completely linear things. Okay, I'm not sure that the spectrum with the perturbation will be exactly the same. So yes, all
When you
the
consider the linear stability, you consider linearization, so you still have a linear
yes,
problem.
yes,
Yeah.
yes, but here the problem will be how to know the exactly quantify the perturbation we use, and this is something that we don't know yet how to do.
Oh.
And also the Gershgorin disk theorem will be not yes, not sure to be satisfied because just can be applied to operator, linear operator, not of on f of u something. So we need to abandon the Gershgorin theorem and just use the counterreach theorem. Okay,
Hmm.
so it's yes,
Yes. Okay. Okay. Thank you.
you're welcome.
So, questions from the audience, comments? Okay, but if this is not the case, so let's thank our speaker. Okay, Maxime Payan again.
Thank you.
Yeah, thank you. Ah, yeah. Very nice, very nice. Yes, so I think this is new to me. This closing diffusion and gauge scoring
Yes, it's
techniques.
new for us too because it was a
Anything.
question from colleagues and Maxime and me yes try to get strategies to say something on this on the spectrum of this
Yeah,
linear
yeah,
operator
yeah.
and yes, fortunately it works. So so yes, we continue in this way and make computations and refine it with Newton counterreach and implicit theorem,
Yeah,
and it was great.
yeah. So in Taiwan, maybe also in Japan, there's a rather big community of traveling wave. So
Okay.
traveling wave or Lotte for Terra or Taylor Ziegler camel
Okay.
taxis. and you can view traveling wave as a so-called relative equilibrium. So it's a steady state in the co-moving frame. Okay, translate. Okay, so there's still the problem of finding the traveling wave and how do you study stability of the traveling wave. But now because the domain is unbounded, it's on the real line. So there's an essential spectrum, there's continuous spectrum, and there's
it's more complicated than
yes,
isolated
AFM's
one
function. Yeah. So I am really looking for if one day I think CAP can already do this somehow. And no. Maybe you can tell me. So can CAP already solve the similar issues like existence and stability of traveling wave?
For traveling wave, I don't know, but there is some results for infinite matrix
Yes.
about the spectrum, etc. But in the literature, I'm not sure that some people use all those tools to get the stability of a system.
Because their scoring is for the isolated eigenvalues, right? If you have like continuous spectrum or essential spectrum,
it doesn't work.
Yeah. So
you need some. Yes, behind the Gauge-Green theorem, there is some hypothesis I hide because they are a little bit complicated. But this notation to be a coefficient a matrix, infinite matrix, is very important, and there is more things also, some compactness, some invertible things. Of the resolvent, etc. So yes, there is some hypothesis behind this that are complicated to satisfy for any case.
Yeah. You just remind me of a question I also asked to Maxime Payan, the other Maxime. So somehow when you want to do the finite approximation of your okay, you have this approximate inverse. Somehow you assume some compactness, right? Some compactness in your problem. But here today I don't really see the compactness somehow where. But this compactness usually is lost for like a wave equation, like hyperbolic equation.
Yeah. Here the
Also
compactness
traveling
is
wave,
hidden.
for example, traveling wave, yeah.
The compactness is hidden in this notation, because if you can write on this in means that you can this is a limit of finite rank operator. Okay, so it's compact. So this is hidden in this. Okay, completely. But of course, in more general operators, you don't have anything, and the spectrum can be continue and etc. With accumulation points, etc. So it will be more complicated, and that's why the Gauge-Green disk theorem doesn't work at all. And you need something more tricky to get some conclusions.
Yes. But sometimes if people just care about like instability, you just need to prove there exists like